The following program is brought to you by Caltech.
Okay, well, it's a very difficult act to follow. I will try my best, but so I thought what I would do is first talk a little bit about Murray from both a general physics point of view and then anecdotal, and then concentrate my talk onto what I call the flavor ring, which is the puzzles that have come up in particle physics from measurements in flavor theory. Most of it having to do with neutrino masses and mixing angles of neutrinos as compared to quark and charged lepton masses, which are some puzzles which have to be explained, and I was kind of hoping that Murray would help. Okay, so what do we do? So first of all, I would like to talk about Murray's vision. I think that looking back and reading a little bit the way people were thinking about stuff when Murray was very young, the importance of symmetries was realized, of course. I mean, there had been symmetries in chemistry, there had been symmetries as part of simplification of calculations, but there hasn't been much of a focus on symmetries as an organizing principle of nature. And I think of his generation, Murray is the prominent example having realized this. And at the time when most people hadn't quite caught on, but of course, after the SU3, strangeness. By the way, Murray, strangeness was not called, your original name for strangeness was not strangeness, right? What? Was it a different name?
No, it had it organized slightly differently.
Because you were rejected by PhysRev letter by the editor, if I recall. And that's what, by...
They didn't like a great deal of the vocabulary.
I see, yeah.
Talked about strange particles, curious particles.
Curious particles, yeah. They didn't like that, no. No, okay. So therefore, physics letter owes the quark paper to this encounter. Okay? And I think quarks are just a brilliant step in that direction of this, basically that there's simplicity, but not only, in Dirac's word, not only simplicity, but beauty in the fundamental interactions. And I think that today, especially the young generation, they may not know much about neutrino mixing angles and stuff like that, but they know a lot about symmetries. And symmetries are viewed as a way of doing theoretical physics, much more than they were. So I think, Murray, your vision continues today as more symmetries are being sought in experiment and certainly exist in the mind of theorists. In fact, it's more, you get more symmetries in the mind of theorists than they are in nature. Okay. So I would like to talk about Murray a little bit. This is purely, this has nothing to do with physics, but it's my interactions with the Grandmaster. So this is a story that was told to me by Lowell Brown, who had a by then very old relative who had been a medical doctor in New York. And in those days, doctors made house calls. And apparently, this doctor related a particular event to Lowell or to his family. And the event went as follows. He was called somewhere in Manhattan. And there was a young kid who had all kinds of symptoms, wasn't feeling well, temperature, et cetera, et cetera. He went to the house. And then the parents were rather eager and said, what's wrong with him, what's wrong with him? And the doctor said, well, you think this is the beginning of bronchitis? And the kid said, no, that can't be it. No, I don't have that symptom. It cannot be it. And so he's so kind of, all right, kid, stay aside. Yeah, and then he continued like this, and of course that was Murray. Murray had gotten all the symptoms, had analyzed everything, and he knew exactly. Maybe he did or did not know. And the doctor, at the end of his life, remembered this encounter because that was unique in his own experience. And this actually sums up Murray. Whether it's true or not, I don't know. My early contact with Murray was a sad occasion when I was a graduate student at Syracuse, and Jack Leitner, one of the co-discoverers of the omega minus, had just passed away at the age of 36. And Murray came for a memorial service. And I was given the task to accompany him to the Everson Museum there. And, well, we all knew about Murray, and we were completely in awe of him. But we did not know he could read, decipher Chinese tablets, because on that museum, there were Chinese tablets. And whether or not he was putting us on or not, I did not know. But obviously, after what I know now, he was not putting us on. And that was kind of the Murray's that I was encounter number 2. The third encounter had to do with what? And that is Murray when basically you tell him something that he has not completely thought about, which happens very rarely. And then there is that what? And then his face, he loses muscular control of his face for a while, and then he recovers rather quickly, and then it's a completely different interaction. Okay. Now, I will recall a compliment from Murray. It's kind of a double-sided compliment. We're working up at Lawrenson, and Murray's his 3-ring binder, and working away, and I'm on the blackboard, and I was in a festive mood at that time, and I start working very, very fast on the blackboard, and then I make a mistake, and then I hear from Murray, "Oh, good. For a moment, I thought you were faster than me." But I view this as I mean, it's okay. Okay? Another one from Murray, which is a bit different, was that Murray learned that I'd spent some time in Mozambique as a child, and I learned some dialects, African dialects. And since I did not continue them during puberty, I lost them completely. And Murray could not believe this. Okay? So we are, with Randy Durand and Bernice, we're having a nice stone crab dinner in Miami Beach. And there it is, and Murray suddenly starts, like a laser beam, boom, some word in some obscure dialect trying to jar my memory. And this went for the whole dinner. And that was a rather memorable dinner. It's true, Murray. Okay. But finally, the Murray effect. For all of us, and you heard a lot of testimonial to that effect, for all of us who have worked with Murray or have collaborated on any kind of ideas and been around Murray, we've all been so much smarter for it. Murray has been basically a man who not only is he very quick, of course he is, but he has the ability to take the garbage away and summarize very quickly what is important. And so you as a normal person, would be basically spending a lot of time recognizing what is important, what is not important. But Murray very quickly was able to focus. And then you had the time to think about important stuff. And therefore you didn't know it at the time, but you were much smarter than normal. And it's the way it was. Okay, so much for that. Now let's talk about rather more boring and more complicated stuff, which is the problem of flavors in the particle physics. Okay, so, all right. So I would like to talk about 2 things. One thing I call flavor ring, and the other thing I call family symmetry, and this has to do with the triplication of families in the world of the standard model. And as I say, we don't know why there are 3 families. It's a bit like a government form in triplicate, and we also don't know why it has to be in triplicate, but it is, and that's the way it is. So we have to understand that it's a problem, a long-standing problem, started with the muon, for which we had no understanding to this day, except we know how to parameterize it. So let me kind of go very, very quickly on this. So we have the world of elementary particles is made up of 3 identical families of quarks and leptons. They're semi-identical. They're actually identical in terms of their interactions, but their masses are wildly different. And those pattern of masses have been something which has occupied a lot of people for a long time. Now, I should tell you that the establishment view of this right now is that it is so complicated that basically no amount of bottom-up physics is going to help you in understanding what is going on. And at some point, somebody will come up with the right theory, and it will come down and they say, this is what it is. But okay, but still you have to try from the bottom up because you are at the bottom of the mountain. So there are three families. They are the top charge and up quark, and maybe the most fascinating thing about it is that the top quark is so damn massive. That is and then this is matched by these quarks and these leptons, and in this case, this is something called the kind of Dirac-like neutrinos. We'll talk about that in a little. And these three things, of course, are what we're made of. And even Murray is made up of those, although I'm not sure. Okay, but anyway, so this is what we have, right? And these, as Murray would say, those are delta I weak equals a half things. They basically all come up from electroweak breaking. Now, there is this Seesaw mechanism that Harold alluded to, which we worked on, which actually had been worked on by Peter Minkowski, who is somewhere there, before us, unknown to us. And I worked with that with Dick Slensky. And the idea was that in some grand unified theory, there was a very massive Majorana matrix of the Majorana type, which basically its presence induces a mixing and makes the normal neutrinos very light. That's called the Seesaw mechanism, and I'll come back to that. But the thing is that this matrix doesn't have any electroweak quantum numbers. It's a beast of a different kind. And the question is, what is the physics behind that matrix? And that's what we would like to understand. Now let's describe the charge 2/3. So there is an angle which Murray doesn't like to call the Cabibbo angle because it appears in a paper with Gell-Mann and Levy, and it's called epsilon. But it is for everybody else, you know. It's a Beatles song, whatever it was. Her name was McGill. She called herself Lil, but everyone knew her as Nancy. Yeah. Anyhow, so a large hierarchy. So up to charm 2T's of order Cabibbo to the 4th. And the -1/3 objects have a somewhat milder hierarchy, only lambda to the 2nd. Those are facts. These are basically as far as we know. Now, why the charged leptons have a hierarchy that's not dissimilar to the one of the charge -1/3, okay? And if you diagonalize both of these, you get an overlap between the two, how they mix, and you get the so-called CKM matrix. The CKM matrix has the characteristics that it's almost equal to 1, and the deviations from 1 are of the order of the Cabibbo angle, and that's basically what people thought was going to happen in a neutrino sector, that basically all the matrices will be almost, and of course there's no reason, this is purely experimental, but these are facts and these have been measured very well. So now enters the Seesaw neutrino mass matrix. The formula of the Seesaw is like this. It's this Y0, that's the neutral Dirac so-called mass divided by this. This is what you get. And you get a new matrix here, which diagonalizes the neutrino. There should be a parenthesis here, okay? And then you got this stuff here like that. And the lepton mixing matrix, which is the matrix, it's called MNSP, MNS, Maki, Nakagawa, Sakata, and P for Pontecorvo, who basically introduced the idea of oscillations in a neutrino sector, except there was the year of the KK bar system, another one of Murray's contribution, and Pontecorvo, because you see Ray Davis had said that there were neutrinos coming out of a reactor in South Carolina, and the border of South Carolina and Georgia, and therefore they had to be anti-neutrino oscillations, and Pontecorvo introduced the idea to the field. But you see what happens here is that this is the observable that our experimental friends have been measuring for a while, and this is what we have. And the most probably, from my point of view, I know the Higgs, Maria likes the Higgs, everybody likes the Higgs, but you know, the fact is that the really very weird experimental result has been that the neutrino masses, as measured, are there, number one, and secondly, a lot of the neutrino mixing angles are large. And those are really, really makes you wonder, and I will explain a little bit why you should wonder. Why, okay. Now, so in my generation, grand unification was a big deal. And I think grand unification should still be a big deal. And in SU5, which is one of the simplest manifestation of the idea of grand unification, the charge minus 1/3 quark mixing and the charge minus 1 lepton mixing are related naively by some sort of transposition. And you find relations like the mass of the B quark is equal to the mass of the tau. Now, as David has just pointed out, of course, the mass of the B quark, you have to define at what scale you measure it. And if it is measured at unification scale, say 10 to the 14 or 15 GeV, these are indeed equal. The renormalization group makes up for the factor of 3 that is viewed in experimental data. That's quite remarkable that this is so close to real life. And then there was a modification in order to get the electron mass correctly, which is called the Georgi-Yarsgaard modification, which was that basically the second, this is where the group theory comes in, the second representation that is in a mass matrix for these guys, okay, because these guys unified both of these, okay, contains this particular relation that basically this is 1/10, and this actually works remarkably well. It's called the Georgi-Yarsgaard mechanism, and it's, as far as I know, pretty good. But then there's another one, and since Fritschkowskis are here, I mean, they're one of the inventors of SO10, okay? There's something quite remarkable, okay? We just talked about the Majorana mass with violates total lepton number by 2 units at the gut scale, but there's something quite nice is that these charge 2/3 objects and the charge 0 Dirac objects, not the physical neutrinos, are kind of related as well by SO10. That's another relation from grand unification. And that's really rather interesting because the hierarchy in a charge 2/3 sector is pretty violent. The top quark is really a very massive object. Okay, and that's a fact of life. So if these guys are related, this is the guy which appears in the seesaw. So that becomes rather interesting. So maybe you might expect that in a seesaw formula, the experimental value that comes out of it will also show a big hierarchy. It does not. So let me now talk about what I call about the flavor ring. So in green, so basically those are the matrices that come out, these matrices come out of the standard model, whatever is the physics that sets them up. They are related in red, this one and this one by SO10, this one and this one by SU5. The experimental data is related by the mixing between the up and down quark, the transition between up and down quarks, and the neutrino are related between the transformation of electrons into the various neutrino flavors. And then we've got this mysterious seesaw, and we've got this Majorana matrix standing there. But as I said before, this Majorana matrix doesn't have anything to do with with the standard model. As we know, it's just an add-on. But nevertheless, how can we find out more about it? Okay, so that's what I call the flavor ring. So let's look a little bit at the data on the neutrino data. So if I write the matrix, the MNSP matrix, so PMNS, by the way, some people like to call it that, but it doesn't matter. So you have different angles, and forget about CP violation in it for the time being. But the angles are large. So these are best fit that came out in a white paper a few months ago. So the best fits are 38 degrees, 33 degrees. This one has just been measured by the Chinese and the Koreans to be very small. And this is the only one that's like, Cabibbo size. Cabibbo angle is 13 degrees or so. Okay, so but these are very big. The mass differences, of course, because the masses only occur right now from basically oscillation experiments are of the order. They don't show necessarily, I guess you could make it because it's only the difference of mass squares, but they don't show the tremendous hierarchy that you find at the top quark being so massive. And then the cosmology, the latest data from Planck tells you that basically the sum of the mass of the neutrinos is less than, it's not a very good bound from this point of view, but a bound it is. Okay, so these are real data, whether one likes to use them or not. This is fine. Okay, so let's kind of summarize where we are. We have a hierarchy of masses, quark and charged leptons, in electroweak breaking sector. We have a Majorana mass we don't know anything about. But the question in a seesaw, remember, if you believe SO10, okay, then the guy on the numerator of the seesaw has a tremendous hierarchy, and yet the mixing data do not show this tremendous hierarchy. So it must be that this Majorana must also show hierarchy, which is very bizarre because they come from different sectors of the theory. So how can we put them together? So let me see. Yeah, so why? Okay, now, so the Murray answer would be let's look for a symmetry. And some people from the very beginning, in fact, Meshkov is one of the, Meshkov and Rosen, I suppose, looked at SU2 family symmetry in a day where there were only two types. But since then, lots of people have looked at such symmetries. And the question is, which one? So Murray's attitude towards that was that, well, there is this tremendous quark hierarchy, and this was in the days where the top quark was not the top quark. In other words, where people knew it was there, but they didn't know how massive it was, that it should be 1, 0, 0. So the question, and Murray said, well, clearly this has got to be like SU3, because only SU3 distinguishes the diagonal elements from the non-diagonal elements, because otherwise you cannot get you can get those zeros, but they have to be very fine-tuned. So therefore, you look at SU3. Now, the second part of the equation, which has come up now, is that basically the large angles in the neutrino mixings, and there are some matrices which look nice, like square root of 2 over 3 and stuff like that, okay, seem to say, well, maybe you can get large values in various things like that if you look at finite groups, back to crystallography fundamentally. So therefore, you should look for finite subgroup of SU3. So this is what we are doing. So let me tell you a little bit about finite groups of SU3. Murray likes group theory a great deal. And, oh, I should tell you a story. At this point, I'll stop, tell a story. So I come up to work. I was at Los Alamos, and Gell-Mann and Slensky are in the same room, and was talking about exceptional groups. And I had learned from Feza Gursey at Yale that we were looking at exceptional groups, and the natural language was Dynkin language. And Murray said, oh, I knew Dynkin, which of course later on I understood to mean he didn't know anything about Dynkin diagrams. I mean, he knew Dynkin, but he didn't, because Dynkin had spent a year at the institute. Dynkin went on to do statistical, different things actually. All right, so what happens is that, so I tell them my attitude towards physics has always been, I'm intellectually lazy, so I try to get away with the minimum amount, okay? And so both of them, the sponge effect came up. I don't know if so those of you have had that with Murray, but when Murray wanted to learn something from you, you were, the bone marrow was the first to go, okay? And it was done very nicely, etc., but that was true, okay? And so there we are. That was a Monday or a Tuesday. And, okay, I gave him everything. I felt, there was just nothing, left of me, okay? Just a few Dynkins here and there on the floor. Okay, but then, so on the Friday, we meet again. And on the Friday, same people, we go there. And then Slensky and Gell-Mann start talking Dynkinese to one another. And I could only catch every third word. It was quite remarkable. Anyway, so finite subgroups of SU3 have been cataloged a long time. There is one particular one here, which actually is the smallest one, non-abelian one. There are many more. I mean, they were cataloged 100 years ago, etc. But just like the continuous group, they distinguish diagonal entries. They have triplet representations. And so the 3 to 3 into 3 symmetric picks up diagonals only, and these guys pick up the off diagonal. So the matter, so if you take this to be a 5 bar, a 10, or a 1 in the grand unified language, take them to be triplets like this. So what you get, well, for example, you take two 10s. These are the guys in which the top quark and his friends reside. So this matrix at the slightest, at the simplest level is diagonal. So if that means 2/3 is diagonal, that means by SO10, 0, Y0D is diagonal, then that means the seesaw matrix looks something like that. It has lambda 16, lambda 81 divided by that mysterious. So the lesson we get from that is that this M must itself be hierarchical tremendously, has to have a hierarchy that cancels this, okay, which we call correlated hierarchy. How can that be? This sounds like magic. Okay? So in particular, if you take the Majorana matrix looking like that, this hierarchy, you can get rid of it, but these coefficients that you get are the ones you measure in the data, and that hierarchy is there, but you don't measure that. So those are the coefficients you measure. And so, for example, the eigenvalues are this. So the eigenvalues are very, very hierarchical. So you say, my God, this is terrible. It's getting worse. But you find the following thing. You find that in this particular matrix, there's a special point at which the subdeterminant becomes 0. Okay? And then you find that the hierarchy is not nearly as much, and it's found to be very unique. So the question becomes, well, what about this? And you see, you look at it with, I'm sorry for showing a numerical thing, but anyway, there's a very, it's a thing of approximation after all. Okay? And the special Majorana matrix one gets looks something like that, lambda c. And this R here has to do with ratio of masses of the heaviest and the lightest. This kind of stuff only occurs for the normal hierarchy, not the inverted hierarchy. And so the eigenvalues, rather than being tremendously spaced, become very close to one another. And this opens the way for people in the field who something called resonant leptogenesis, actually, which is very interesting. Okay, so this matrix comes up very kind of nicely, and it reproduces what's known as the tribimaximal mixing with A equals 1, which is a matrix I think that was studied by Sid and Peter in the context of quarks, because, but this is in the context of neutrinos, where the angles are, well, you will see what the angles are in a moment. Okay, so that's what it is. So, for example, in that particular matrix, the matrix of the seesaw is at its angles are 35 degrees, 45 degrees, and eta 1,3 is 0. But yet, the MNSP matrix is not exactly that. It is the charge lepton matrix multiplied by this. This is what we call Cabibbo haze, because this charge lepton from the grand unified stuff has lots of Cabibbo angles in it. So we think that what you're measuring here is a reflection of this seesaw matrix, but together folded in with this neutrino effect. And some people have been saying, why should we measure those angles with greater accuracy? I say we should. So for example, this Cabibbo haze, let me give you an example what happens here. Remember the Cabibbo angle is about 12 degrees. Okay? So if I look at delta ij to be the experimental value minus this, you find those angles 3 degrees, 7 degrees, or 9 degrees. So they're all small on the scale. Well, they're all smaller than. So it's almost 1. So which is not inconsistent with the idea of that, okay? And that comes from lepton mixing. Okay, so now comes so this is all numerology and stuff. But now comes the idea, can we actually get this matrix from a symmetry? And the answer is yes, which is kind of remarkable. Remember, with the subdeterminant being 0, which is kind of bizarre, okay? So it turns out that if you look at, for that you have to introduce fields, which people in that business do. They're called familons. These are guys which have no quantum numbers except family quantum numbers. And you look at dimension, this would be the right-handed neutrino guy. And this particular coupling scheme, which we call a nesting, this is a higher dimension operator, reproduces that matrix. And there are about 300 or 400 such couplings that are invariant under that group, and one of them only reproduces this. So, does it mean anything? I don't know. So this one coupling is family invariant, and then the whole hierarchy comes from the vacuum expectation value of the familons. So that means that you are going into an extreme case where the physics, the couplings between the visible sector and the familon, there are very few of them, and the familon physics we don't know anything about, and everything is in a vacuum, which is, a logical possibility. So what it looks like right now is something like this. We have the standard model. We're studying this now in greater detail. We're kind of amazed that this is actually has gone that far. But I want to say that the business about following the hierarchy in those two sectors through the seesaw, I think, is something one should do. So what we have now, we have these familons, and we don't know their physics, but we begin to know their vacuum values, which means that we may be able to reconstruct their potential. Okay? And then they give masses to this. There are people here. There's another hidden sector which people use for supersymmetry, for example, which also gives masses, injects masses, like a doctor injects drugs into the standard model. Okay? And hopefully, but then of course, one thing that is also interesting, maybe these two sectors may not be unrelated, which is an interesting. Anyway, we have lots of hidden sectors. And of course, together with the cosmological constant, we probably have even more hidden sectors because the whole thing is kind of complicated. But so what this means is that if flavor physics, if there is a bottom-up view on flavor physics, this is giving us this kind of picture. We will never know probably what this is unless somebody comes from the top down on this theory. But the fact is that the structure that we observe seems to get more or less reproduced by higher dimension operators, which means we're integrating over something. We don't quite know what it is. So this is where that is. So this is what I do for a living right now. So it's getting to be lots of fun. But my own feeling is that, yes, I mean, there are a lot of people looking for the next, getting ready for the next CERN experiment and doing this and that. But the two really spectacular measurements of neutrino masses, neutrino mixings, and lately the value of the reactor neutrino is remarkable because there was a sociological fixed point. That theta 1,3 has to be 3 degrees, but it's 9 degrees. Factor of 3, maybe. We don't know. But no. That's correct, and it's probably continue. Well, yeah, but no. In flavor, you got to be careful. In flavor, you say something, and it works in a very limited case, and then you generalize it, and it doesn't work. Until you have a theory, you cannot really single out anything. Even though, yes, I mean, but the one thing I would say that is important is that the deviation. If you have a very beautiful seesaw matrix that is determined by symmetry, and coming from then the experimental stuff, you should look at the experimental stuff minus the prediction of that matrix, and that will tell you about charge lepton physics. That
What's the last word?
hidden sector. Oh, this is. Oh, sorry. Ooh, excuse me. Sector. That was a C, but I am not like Oguri. I cannot write very well on a tablet. Oguri's writing looks like a font. Okay? Mine is pathetic. This is, so, yeah. Okay. So there are lots of hidden sector, but the question is, everything now in physics comes down to, yes, there are symmetries perhaps, but what breaks those symmetries? And we have absolutely no idea. It's an experimental question. But of course, the symmetries may not even be there, which is also true. Okay, so I want to show a paper. This is a paper that we wrote a long, long time ago, and it was, well, it could have been written much sooner had Murray basically agreed. Eventually, so I wanted to show you something here. So this is the one where we're talking, this is where the seesaw, the seesaw mechanism appeared, but other things as well. And Murray, in this, gives his encyclopedia, his summary of knowledge as of that date, essentially. And we followed along. But he says, Pierre, last corrections. Yeah, sorry, this is so disorganized. Yeah. Better next time, perhaps. Unfortunately, there was no next time. Our path diverged, and Dick is no longer, Dick Stansky is no longer with us. But I just wanted to tell you about, first of all, how it looks. So, given my African background, Bwana, un dio Bwana. It was, you know, it's been, when you offered me that job at Caltech, I mean, that stuff, I couldn't believe it. And I must tell you, I like sports, you know, and I feel like perhaps, you know, maybe for a while I played on the same basketball team as Michael Jordan. And that was quite a treat. Thank you.